Chapter 3 Stoichiometry Calculations with Chemical Formulas and Equations. Pour vinegar into a glass of water containing baking soda, and bubbles form. You strike a match and use the flame to light a candle. You heat sugar in a pan and it turns brown. The bubbles, flame, and color change are visual evidence that something is happening. To an experienced eye, these visual changes indicate a chemical change or a chemical reaction. Some chemical changes are simple, others are complex. Some are dramatic and some are very subtle. Even as you sit reading this chapter, chemical changes are occurring in your body. Those occurring in your eyes and brain, for example, allow you to see these words and think about them, although not as obvious as those we see. In the laboratory, the chemical changes taking place in our bodies are nevertheless remarkable for how they allow us to function. In this chapter, we'll explore some important aspects of chemical change. Our focus will be on the use of chemical formulas to represent reactions and on the quantitative information we can obtain about the amounts of substances involved in reactions. Stoichiometry is the area of study that examines the quantities of substances consumed and produced in chemical reactions. Stoichiometry provides an essential set of tools widely used in chemistry, including such diverse applications as measuring ozone concentrations in the atmosphere and assessing different processes for converting coal into gaseous fuels. Stoichiometry is built on an understanding of atomic masses, chemical formulas, and the law of conservation of mass. The French nobleman and scientist Antoine Lavoisier discovered this important chemical law during the late 1700s. Lavoisier stated in his law in this eloquent way, "We may lay it down as an incontestable axiom, that in all the operations of art and nature nothing is created. An equal quantity of matter exists both before and after the experiment. Upon this principle the whole art of performing chemical experiments depends." With the advent of Dalton's atomic theory, chemists came to understand the basis for this law. Atoms are neither created nor destroyed during a chemical reaction. The changes that occur during any reaction merely rearrange the atoms. The same collection of atoms is present both before and after a reaction. Figure 3.1. Antoine Lavoisier, 1734. The science career of Lavoisier, who conducted many important studies on the combustion reactions, was cut short by the French Revolution. Guillotined in 1794 during the Reign of Terror, he is generally considered the father of modern chemistry because he conducted carefully controlled experiments and used quantitative measurements. Section 3.1. Chemical Equations. We represent chemical reactions by chemical equations. When the gas hydrogen burns, for example, it reacts with oxygen in the air to form water. We write the chemical equation for this reaction. 2H2 plus O2 yields 2H2O. We read the plus sign as reacts with, and the arrow as produces. So restating, two molecules of hydrogen reacts with one molecule of oxygen to produce 2 molecules of water. The chemical formulas on the left of the arrow represent the starting substances, called reactants. The chemical formulas to the right of the arrow represent substances produced in the reaction, called products. The numbers in front of the formulas, called coefficients, indicate the relative numbers of molecules of each kind involved in the reaction. As in algebraic equations, the coefficient 1 is usually not written. Because atoms are neither created nor destroyed in any reaction, a chemical equation must have an equal number of atoms in each element on each side of the arrow. When this condition is met, the equation is balanced. On the right side of equation 3.1, for example, there are 2 molecules of H2O, each composed of 2 atoms of hydrogen and 1 of oxygen. Thus, 2H2O, read 2 molecules of water, contains 2 times 2 equals 4 atoms of hydrogen, and 2 times 1 equals 2 oxygen atoms. Notice that the number of atoms is obtained by multiplying each subscript in a chemical formula by the coefficient for the formula. Because there are 4 hydrogen atoms and 2 oxygen atoms on each side of the equation is balanced. Balancing equations. Once we know the formula of the reactants and the products in a reaction, we can write an unbalanced equation. We then balance the equation by determining the coefficients that provide equal numbers of each type of atom on the 2 sides of the equation. For most purposes, a balanced equation should contain the smallest possible whole number coefficients. Figure 3.3. The difference between changing subscripts and changing coefficients in chemical reactions. Changing a coefficient changes the amount of molecules. 2H2O means 2 water molecules that each contain 2 hydrogen and 1 oxygen. H2O2 means 1 molecule of hydrogen peroxide, which contains 2 hydrogen atoms and 2 oxygen atoms. In balancing an equation, you need to understand the difference between coefficients and subscripts. Figure 3.3 illustrates changing subscripts in a formula from H2O to H2O2, for example, changes the identity of the substance. The substance H2O2, hydrogen peroxide, is quite different from the substance H2O, water. Never change subscripts when balancing an equation. In contrast, placing a coefficient in front of the formula changes only the amount of that substance and not the identity of the substance. Thus, 2H2O means 2 water molecules. 3H2O means 3 molecules of water, and so forth. To illustrate the process of balancing an equation, consider the reaction that occurs when methane, the principal component of natural gas, burns in air to produce carbon dioxide gas and water vapor. Both products contain oxygen atoms that come from O2 in the air. Thus, O2 is a reactant. An unbalanced equation is methane plus oxygen yields carbon dioxide plus water. It's usually best to balance first those elements that occur in the fewest chemical formulas in the equation. In our example, carbon appears in only 1 reactant and 1 product. The same is true for hydrogen. Notice, however, that oxygen appears in 1 reactant and 2 products, so let's begin with carbon. Because 1 molecule of methane contains the same number of carbon atoms as the molecule of carbon dioxide, the coefficients for these substances must be the same in the balanced equation. Therefore, let's start by choosing the coefficient 1, unwritten, for both methane and carbon dioxide. Figure 3.4, methane reacts with oxygen in a Bunsen burner to produce carbon dioxide and water. Next, we focus on hydrogen. Because methane contains 4 hydrogen atoms and water contains 2 hydrogen atoms, we balance the hydrogen atoms by placing the coefficient 2 in front of the water. Then there are 4 hydrogen atoms on each side of the equation. Unbalanced, methane plus oxygen yields carbon dioxide plus 2 waters. Finally, a coefficient of 2 in front of the O2 balances the equation by giving 4 oxygen atoms on each side. Methane plus 2 molecules of oxygen yields carbon dioxide plus 2 molecules of water. The molecular view of the balanced equation is shown in Figure 3.5. Figure 3.5, balanced chemical equation in the combination of methane. 1 methane molecule plus 2 molecules of oxygen yields 1 carbon dioxide molecule plus 2 molecules of water. Indicating the states of reactants and products. Symbols indicating the physical state of each reactant and product are often shown in chemical equations. We use these symbols, G for gas, L for liquid, S for solid, and AQ for aqueous, for a gas, liquid, solid, and aqueous, which is water, solution respectively. Thus, equation 3.4 can be written: methane gas plus 2 molecules of oxygen gas yields carbon dioxide gas plus 2 molecules of hydrogen of water in gas, water vapor. Sometimes the conditions under which the reaction proceeds above or below the reaction arrow. The symbol delta above the arrow indicates addition of heat.